Good morning, students. In our previous classes, we will discuss in detail. We discuss the effects, that is the experimental observation of the photoelectric effect. So that one is very important for 3 marks. So in detail, we make the key points on experimental observations of photoelectric effect. Experimental observations on photoelectric effect, right? So in detail we discussed how the photocurrent will vary with respect to frequency, vary with respect to potential difference, and vary with respect to the material which we use for the photosensitive material. So those are the experimental observation we did. So in that, if we make the points, means in that first point is the photoelectric effect is an instantaneous process, right? So for all the experiments, whenever the frequency which incident above the threshold frequency, then the electrons are emitted from the photosensitive material or photosensitive plate. So the emission of the electron will take less time of the order 10 to the power of -9 second or less. Hence, we call the photo emission is very instantaneous process. So, whenever the frequency which falls above the threshold frequency or cutoff frequency, then the electrons are emitted within less than this much of time. So, hence we call the photo emission. That is, the photoelectric effect is an instantaneous process of the order. It takes time 10 to the power of -9 second or less than this time, right? So if you make the point, the photoelectric emission is instantaneous process of order 10 to the power of -9 seconds or less, right? So this one is the first point. So in this point, the photoelectric emission or photoelectric effect, that is instantaneous process. Within short time, when the frequency greater than the threshold frequency, the electrons are emitted. So for that reason, we say that the photoelectric emission we call as instantaneous process, right? So we move on to the second. For a given photosensitive material, there exists a minimum frequency called cutoff frequency or threshold frequency. So it is denoted by mu naught, right? For a given photosensitive material, there exists a minimum frequency. That frequency we call as cutoff frequency or threshold frequency. So in this, below this threshold frequency, there will be no photo emission, right? So this one is the second point. For a given photosensitive material, there exists a minimum frequency. That minimum frequency we call as threshold frequency or cutoff frequency, right? So that minimum frequency we call as threshold frequency or cutoff frequency, which is denoted by nu naught. So here 0 is in the suffix. That one is the nu naught. For this threshold frequency, that is below the threshold frequency, that means nu is less than nu naught, then there will be no photo emission, right? So if we plot the graph for this statement, so along x-axis we taken frequency of incident radiation, that is nu. Frequency of incident radiation. Along y-axis we taken this one as photo current. There will be no photo emission is nothing but there will be no flow of current in the external circuit, then there will be no current. So if you plot the graph, so this gives the current. So here this point will be denoted by nu naught. Nu naught represents what? Threshold frequency. Right. So this is for what? Nu is greater than nu naught. Whenever nu is greater than nu naught, then only the emission of photo electrons takes place. Then only the photo emission takes place. So here nu is greater than nu naught. That is towards right side of this linear curve. Towards left side there will be no photo emission. Right? So nu naught is the threshold frequency. Next, for threshold frequency, the stopping potential or recording potential is 0. That is kinetic energy gained by the photoelectron depends or varies linearly here it is, maximum kinetic energy. Maximum kinetic energy gained by the photoelectron varies linearly with the frequency of incident radiation, and it is independent of intensity of incident light. So this one is the second point. So in this second point, it states that the threshold frequency, for threshold frequency, the stopping potential is 0. Nothing but V naught is equals to 0. So that means we can also say this one, that is stopping potential is 0, is nothing but the kinetic energy gained by the photoelectrons varies linearly with the frequency of the incident radiation. That is, as the frequency increases above the threshold frequency, then automatically the energy of the electrons also increases. Then only the photocurrent increases. Right? So this one is the second sub-statement of this statement. That is, depends on the frequency. So if we plot the graph for this one, so this one is the photocurrent. stopping potential. And here is the frequency. Frequency of incident radiation, then curve is like this. So here this point is nu naught. So here nu is greater than mu naught, right? So this curve represents the linear curve. As the frequency increases, then automatically the stopping potential increases. That is nothing but as the potential increases, then the kinetic energy also increases of the photoelectron, right? This varies linearly with the frequency. That is kinetic energy varies linearly with the frequency and it does not depend on the intensity. So this one is the second point, right? So this one is very important for 3 marks, 7 and 10 they ask. So if the question asks experimental observations of, write the experimental observations of photoelectric effect, means you have to mention these points, right? So first point is the photoelectric emission is instantaneous process of order 10 to the power of -9 seconds, and second one is for a given photosensitive material there exists a minimum frequency called cutoff frequency or threshold frequency. Next, below the threshold frequency there will be no photo emission, right? Below the threshold frequency there will be no photo emission, and for a threshold frequency, the stopping potential is 0. So here to here, that is the curve is here. So from here to here, the stopping potential is 0. After the threshold frequency, the kinetic energy gained by the photoelectrons varies linearly with the frequency of the incident radiation. So this one is the second point. So if you move on to the third one. So this point is very important. So by using this point, we will discuss few concepts in later classes. That is, kinetic energy of the photoelectron depends on the frequency, not on the intensity. Next, third point, for a given photosensitive plate, for a given photosensitive plate, the photocurrent proportional to intensity of incident light. So this one is the third point. For a given photosensitive plate, the photocurrent is proportional to the intensity of the incident light. For this, if we plot the graph, means so along x-axis we taken intensity of incident light or radiation. So along y-axis photo current, then the curve is like this. So this one is the third point. For a given photosensitive plate, the photocurrent is proportional. This photocurrent is proportional to intensity of the incident radiation. If the intensity is 0, then photocurrent also 0. If intensity is 5, then photocurrent is also 5. That's why it varies linearly, right? So this one is the third point. And the fourth point is, if positive potential is applied to the collector plate and otherwise positive potential is increasing in collector plate then photocurrent also increases. For a particular also increases and becomes maximum. Right, like that. Increases and becomes maximum. So if we apply the positive potential, that is apply the positive potential to the collector plate and we increasing that potential, then the current also increases and becomes maximum. So this maximum current we call as, so this maximum current called as saturation current, right? So here in the experimental we have two plates, one is photosensitive plate and another one is collector plate. So we are applying the potential to the collector plate, that is positive potential, and keep on increasing the potential values, then automatically the current also increases and becomes maximum for a particular potential. So that current we call as saturation current. So in the second one is, if negative potential is applied to the collector plate, then the photocurrent decreases rapidly and becomes zero for a particular negative potential called stopping potential. So this one is the fourth point, right? So here first we apply the positive potential to the collector, right? Next we are applying the negative potential, right? So here we apply the positive potential to the collector plate and increasing. Here we apply the negative potential to the collector plate and we keep on increasing. So as we apply the negative potential to the collector plate, then the photocurrent decreases and rapidly becomes zero. So decreases rapidly and it becomes zero. So for which potential the photocurrent becomes zero, then that potential we call as stopping potential. Right? So these are the four experimental observations while studying the photoelectric effect. Right? So this one is very important for 3 marks. So continuously back to back they ask the question. So if you plot the curve for this one, that is potential versus photocurrent, then photocurrent we take up along y-axis, and here it is 0 towards right, collector plate potential, and here it is retarding potential or negative potential. So if I plot the graph for this one, so this is so this point we use the name, that is VO, stopping potential, right? So these are the experimental observation, right? So we have to practice these 4 points along with this graphs, right? So this is very important for 3 months. If they ask for 3 months, you have to mention any 3 points out of these 4 points, right? So this is clear. These are the experimental observations of the photoelectric effect. So next topic. So next concept is wave theory and photoelectric effect. So in the last chapter we discussed in detail the wave theory. So wave theory satisfactorily explains the phenomenon of interference, diffraction and polarization, right? So we need to check here whether the wave theory will explain the photoelectric effects. That is, we did the experimental observation. Here we have the 4 points. That is, the experimental observation will be satisfied by this wave theory or not. So light is considered as a wave, that is electromagnetic wave in which it contains the electric and magnetic fields, right? So in wave theory, light is considered as electromagnetic wave, right? So in wave theory, considered as light is considered as the electromagnetic wave. So electromagnetic wave is nothing but it contains both electric field and magnetic field, right? So its intensities depends on throughout the in space. Its intensity is depend on throughout the wave form, right? So this is about the wave as we discussed in the wave theory. That is, light is considered as the electromagnetic wave. So electromagnetic wave consists of electric field and magnetic field. These intensities in the space will be formed throughout in the wave, right? Next, so this wave, that is electromagnetic wave, consists of electric field and magnetic field. Then the intensity and energy. The intensity and energy of the wave depends on amplitude, right? So this one we say that this is the form of wave, then this wave has the amplitude, we call that one as A, right? So the intensity and energy of the wave depends on what? Amplitude, right? So intensity is varies to the square of amplitude, and also the kinetic energy, that is energy is kinetic energy, also depends on the square of the amplitude, right? So from the wave theory, here we can say that the intensity will increase, that is the energy here. If you observe here, the intensity, if the amplitude is more, then the intensity will increases, or if amplitude is more, nothing but its kinetic energy also more. So in wave theory, we consider the intensity and energy of the wave, which depends on the main factor, that one is the amplitude. Hence, the energy of the photoelectrons depends on the intensity, right? Because here intensity depends on the amplitude and energy also depends on the amplitude. Then the energy of the photoelectrons depends on the intensity. So in wave theory, the energy, or we say that this one has kinetic energy. Kinetic energy of electrons or photoelectrons depends on the intensity, right? This is we studying in the wave theory. Intensity depends on the amplitude square, and also kinetic energy also depends on the amplitude square. Then we say that intensity is depending on the kinetic energy. So this means that kinetic energy of the electrons directly depends on the intensity. But this statement is contradicts to as we studied in the experimental observation. So in experimental observation, what we studied means the kinetic energy of the photoelectrons which are emitted from the photosensitive material is directly, that is, it depends on the frequency, right? So it depends on the frequency, it will not depends on the intensity of the radiation, right? So this statement is contradiction to the as we studied in experimental observation. So wave theory states that the kinetic energy directly depends, or it depends on the intensity, because the intensity and energy both are depends on amplitude, right? As you already studied in previous class, that is in sounds, we note the relation, that is energy of the wave and also intensity of the wave, which these two factors directly depends on the amplitude. So hence the kinetic energy of the electrons is directly depends on the intensity. But what we studied in the experimental observation means the kinetic energy depends only on the frequency of the incident radiation, not on the intensity. That is, it is independent of the intensity. Hence, it fails. Wave theory fails to explain this statement. Right? So this one is the first point. So first point is the kinetic energy is depends on the intensity, but in experimental observation we did is the kinetic energy of the electrons depends on the frequency of the incident radiation, not on the intensity of the incident radiation. So this one is the first point. Next, according to wave theory, there is no relation between energy and intensity. So not intensity, energy and frequency, right? So in the first point, according to wave theory, kinetic energy of the electrons depends on the intensity, but in the experimental study, this is not true. That is, this statement is contradiction to that of the experimental study, right? So here in the second statement, that is, according to the wave theory, there is no relation between the energy and to the frequency, right? The kinetic energy is directly depends on the frequency from the experimental observations, but here in wave theory we don't have any energy to the frequency relation. That is nothing but there is no, according to this statement, according to this wave theory, so there is no threshold frequency, right? So there is no threshold frequency. So if there is no threshold frequency, nothing but we can't plot the graph, that is photo current versus the frequency, right? So here, if the frequency is more than threshold frequency, then only the electrons are emitted from that metal plate or photosensitive plate. So if there is no threshold frequency, is nothing but there will be no concept of this statement, right? So this is also contradictory to that of the experimental observation. So second point is, according to the wave theory, there is no relation between the energy and the frequency, right? So for this, there will be, according to this, there will be no threshold frequency. If there is no threshold frequency, then the electrons will not attain any energy. Hence, those statements which we observed in the experimental observation will not satisfyly explained by this wave theory. So this one is the second point. And the third one is, that is, we state in the first point of the experimental observation, that is, photoelectric emission is instantaneous process, that is, it takes the time of the order 10 to the power of minus 9 seconds. But here, if you observe, if you consider this one is the metal plate, right? That is photosensitive metal plate. So, wave, according to wave theory, the waves are in the form of wave front, right? So that is like this. So when the wave fronts incident on this photosensitive plate, right? So this photosensitive plate contains number of electrons, right? So this contains very large number of electrons. So the energy of this wavefront, right? So this wavefront, when incident on this photosensitive plate, if you observe here, we have this much of the photosensitive plate, and here we have the wavefront. So these are the wavefronts, right? So wavefronts nothing but here we have the energies. So energies contained in this wavefront. Then if you observe, each electron will get only the part of the energy of this wavefront. So are you understanding this? Each electron, that is, each electron gets, this one is the overall energy, right? So if you consider this one as energy E of this wavefront, when this energy will fall onto the photosensitive plate, the electron which are present in this photosensitive plate will not absorb, that is, each single electron will not absorb the energy E. That is, only part of this energy is absorbed by this electrons, because here we have number of electrons. So according to the wave theory, the wavefront consists of the energy E here, right? So this energy is not fully absorbed by the single electron. So only the part of the energy is absorbed by the each electron. So hence the energy gained by the electron, that is, per unit time is very less, right? So this one is the first one, right? So each electron gains energy, that is it will not full energy because this energy is divided to all the number of electrons, because this wavefront contains the energy. So here we have, if we consider we have 10 electrons, then here we have the energy, for example 100 joules of energy we have in this wavefront, then we have 10 electrons, then each electron will get, that is 100 divided by 10 is 10 joules of energy is getting by the each electron per unit time. So for 1 second, one wavefront will be incident on this photosensitive plate, then it occurs only the 10 joule, but actual energy of the wave is how much? It is 100. So by this we can observe that for one single electron to gain the minimum energy, that is the work function to which will come out from this metal surface, that is the energy which is greater than the frequency, which is greater than the threshold frequency, nothing but here the work function, the energy gaining by this electron has to, for example here the emission, right, of this electron, that is work function pi naught, for example it is 2 electron volt, right? So each time this electron is getting only 0.1 electron volt, that is for each time the wavefront incident on this electron, then it has to wait for how much time? Up to we need 2 electron volt, that is it takes more time to get the work function, right? That is it takes more time to get the minimum energy to escape from that metal surface, right? So it may be minutes or it may be in hours. So each electron has to wait more time to get the work function or to get the minimum energy, then the time will be more. So this is also the contradiction to the first experimental observation, that is the photoelectric emission is instantaneous, that is of the order 10 to the power of minus 9 seconds. But here according to the wave theory it may take several minutes or it may take several hours to emit the electron, because here each electron per unit time the energy getting is very less. To gain the maximum energy, that is minimum energy to escape from this metal surface, has to take more time, right? So more time. So this is contradiction to this one. Hence from the wave theory it can't prove that the emission, that is photo emission, is instantaneous process. So by all these three observations wave theory fails to explain the photoelectric effect, right? So wave theory fails to explain the photoelectric effect. So this one is the conclusion. Wave theory and photoelectric effect. So here we have the experimental observations of the photoelectric effect. So in that first observation is, that is experimental observation, photoelectric emission is very instantaneous process, that is on the order 10 to the power of minus 9 second, or it may take more or less than this one. But according to the wave theory, for the emission of the photoelectrons, so each electron has to wait more time to get the minimum energy to escape from this metal surface, right? So for that reason it will take more time, hence it is contradictory to the experimental observation. So next one is the energy and intensity depends on the amplitude in wave theory, hence the kinetic energy depends on the intensity, but our experimental observation says that the kinetic energy of the photoelectrons depends only on the frequency of the incident radiation, not on the intensity, right? So that one also fails to explain by the wave theory. And the third one is there is no relation between the energy and frequency. Hence, there will be no concept of the threshold frequency and there will be no concept of the stopping potential. Hence, that also fails to explain the concepts of stopping potential and saturation current and threshold frequency. So, by observing or by explaining these three concepts, we can say that is wave theory fails to explain the photoelectric effect. But wave theory successfully explains the phenomenon of reflection, refraction, interference, diffraction, and also polarization. Right? So this is about the wave theory and photoelectric effect. So key points are it fails to explain the relation between the energy and intensity, and it fails to explain the instantaneous process of photo emission, and the third one is the threshold frequency. That is, there is no relation we find between the intensity and to that of the frequency of the incident radiation. So by this, wave theory fails to explain the photoelectric effect, right? So this is the synopsis, or this one is the explanation of this wave theory and photoelectric effect, right? So in our next class we will discuss the Einstein's photoelectric emission. So it changes over this concept and he given one equation. So until now we don't have any, in the experimental observation we didn't get any relation, that is in the mathematical relation of the photoelectric effect. So Einstein's given that one in the mathematical expression. So in the next class we will discuss the concept, that is Einstein's photoelectric effect. So we have to clear that we have two experimental observations. One is Einstein's photoelectric effect observation and also the normal experimental observation. In the examination, we have to clearly observe that only they ask the observations on photoelectric effect, or they may ask the Einstein's observation on photoelectric effect, or Einstein's equation on photoelectric effect. Right? So don't get confused on these concepts. Right? In the next class, we will start with Einstein's photoelectric equation. Thank you.